That this section is about Pascal's triangle. We're going to start out by talking about something kind of offbeat, you know, a little bit fun, I hope. The lottery and other things like that. So what's the connection? Well, it's going to take a while before we make that connection. But right now I want to start out with something that you'll see if you take my statistics class this fall, which is the combinations formula. Combination formula says if you're going to choose R objects from a group of N objects, how many choices do you have? So for instance, how many cards are there in a standard deck?
52.
52. And typically if you play poker, you deal out 5 of them. So if you have a well-shuffled deck, how many ways are there that you can deal out those cards? Well, the answer to that would be 52, choose 5. 52, choose 5. Now, that's the notation. That's one notation for it. Here's another notation. 52, choose 5. So depending on where you're at, you'll see different notations. Now the calculation that goes with that looks like this. It's going to be 52 factorial over 5 factorial times 52 minus 5 factorial. And that can be a lot. Let's try and remind ourselves, first of all, though, what 5 factorial is. I think I've talked about this before. You remember what that would be, 5 factorial, or how you would calculate it or work with it?
It's like 5 times 4 times 3 times 2
Yeah,
times 1.
5 times 4 times 3 times 2 times 1, or 120. Now, what 5 factorial itself represents, or n factorial represents in general, is how many different ways you could arrange a group of 5 objects. So if I had 5 students across the back row, I have 5 choices for the first seat, then 4, then 3, then 2, then 1. There'd be 120 ways that I could arrange those 5 students. Now, this is a number that gets really big really fast. So let's play around with it a little bit before I tell you how you can calculate this with just a push of the button on your calculator. Let's suppose that you're watching the Tigers more often now because they're actually somewhat good, and you want to figure out how many ways there are to line up the starting lineup and the manager from first base to home plate to stand for the national anthem. So that would be 10 factorial. So it'd be 10 times 9 times 8 times, oh man, it doesn't look very fun to calculate that manually. So in fact, I don't see a lot of people rushing for their buttons. So let me show you how you can calculate that on your calculator. First of all, let's type in the number 10. Then hit the math key. Except we don't want to find this off the math menu. You'd go over to the probability menu. Does it look like there's something interesting or helpful on the probability menu? Yeah, maybe the 4th option. Now, before you hit the enter key, try and guess how many people, or how many different ways you think there are we can arrange 10 people. I bet that it's bigger than what most of you would imagine. Over 3.6 million different ways we could line up those 10 people from home plate to first base. Wow. Factorial is a number that gets really big really fast. So it's kind of cool. And in particular, one of the cool things you can do with it is what we want to do with it here is calculate, say, 52, choose 5. So how many different ways are there, do you think, that you can draw 5 cards out of a well-shuffled 52 card deck? Well, calculating this by hand or not by hand, well, mostly by hand would be kind of a pain, but with our graphing calculator, it's not so bad. Let's type in the 52 first. So 52, and then let's see, let's go to the math key. Where did I go last time? Probability. So cursor over to the left 2, and then you see, oh, NCR. Now if you want to know what NPR is, and I don't mean National Public Radio, if you want to know what NPR is, you're going to take my statistics class this fall. But right now, you got about 2.6 million different ways you can draw 5 cards out of a standard deck of 52. Wow. So this shows you the odds of getting a royal flush on the deck would be about 4 out of that many. If you get a royal flush on the deck or off the deal, you're really lucky. So, nice. So let's see, 52 choose 5, about 2598960. Let me write that down. 2598 960. So are you able to get that number off your calculator? All right. So that's kind of an important thing here. One of the easy questions that I could ask would be something like this: calculate 5, choose 3. So why don't you give that one a try in your calculator, see what you can come up with. Is it worth it to be able to calculate by hand? It's nice. You don't have to.
Wait, what's the exclamation point called again?
A factorial. So, you know, I guess it's context dependent. In a math class, this is 5 factorial. In an English class, this is 5. I can't help myself when I cover this stuff. I always got to slip in that joke because it wakes up a few of you, Rachel included.
Thanks so long.
No problem. So what are you getting from this one here? Example B. 10. Good. You should get 10. Now, why are we worrying about this kind of stuff? Well, I'm going to get there kind of slowly. It's going to start with a desire to be able to do things like this a lot faster. If I had 2x minus, let's say, 5y to the 5th power, if I wanted to figure out what this is, well, on the surface of it, that looks like a lot of work. Because keep in mind what you would have to do. You'd have to take 2x minus 5y times 2x minus 5y 5 times, and multiplying that all out the long way would be a real drag. Let's remind ourselves what a smaller problem would look like. For instance, a plus b squared. So just the first part of what we'd have to do up above. That'd be a plus b times a plus b. And we'll just FOIL this all out. What do I get when I combine like terms here? Good. A squared plus 2ab plus b squared. Now I threw in some coefficients there just for effect. But what I want you to notice is that those coefficients are right here. And if I cube this out and did all the work there, those coefficients are here and here and here. In fact, let's just look at the coefficients for just a moment. And if you look at the coefficients, then you're going to move from here over to here. Now, if you're worried, like, I don't have this handout, don't worry. Number one, I'll put it in the notes. Number two, you don't really need it. But take a look. This is what's called Pascal's triangle. Now, it's named, ironically, after Blaise Pascal, who was a 17th century philosopher and inventor, although he didn't discover it. He just got his name attached to it somehow. Okay, good for him. That's not the only time in history that kind of thing has happened. In any case, this is Pascal's triangle, and what these numbers represent are the coefficients of your binomial expansions. Now, when we look at our binomial expansions, for instance, a plus b to the 5th power, well, you see all these coefficients, but there's a little bit more going on than just the coefficients. Take a look at the exponents. We've got a to the 5th, a to the 4. Is there a little pattern with the coefficient or the exponents for the a's? 5, 4, 3, 2, 1, and then 0, right? Anything to the 0 power is 1. If you work with the b's, then what happens with the b's? Well, b to the 5th, b to the 4th, b to the 3rd, b to the 2nd, b to the 1st, and then b to the 0 power. So those exponents start from this one and decrease down, or this one and go down the other way, or you can say the increase. Either way. But if you take a look at the total of these, 4 and 1, 3 and 2, 2 and 3, 1 and 5, 1 and 4, what do they always total up to? This one right there. So there's a pattern to this. And if you know the pattern of the exponents here, And if you know the coefficients for Pascal's triangle, then great. Then you can expand these binomials a lot faster than having to multiply it out by hand. So, the big question is, well, how do I get these levels of Pascal's triangle? So, to get like the next level, what you're going to do is you're going to put a 1 on the outside of each of these. And how about the numbers in between? How do you think I'm going to get those? Like, for instance, what should I put right here? 6. Where'd you get that 6? Yeah, add these two together. You get a 6. And then these two together. 15, 20, 15, and 6, and 1. And so, wow. So you can get as many levels as you want in Pascal's triangle. And Pascal's triangle's got a ton of nice little patterns in them. I'll go over a few of them. Yes?
This kind of is similar, at least from my perspective, to the golden ratio.
Yeah, it does tie into the Fibonacci numbers, which we discussed, and it does tie into a lot of things. Let me just share with you a couple of the patterns that you'll get on Pascal's triangle. So one of them, if you look at these right here, these numbers are your so-called triangular numbers. And what's interesting about those triangular numbers? Those are numbers that you get when you arrange things in kind of like stacks. So for instance, we'll start out with a 1, then you can do a 1 like this, or 1, 2, 3. So 1, 3, 6. What's the next one if I make a stack 4 wide? How many am I going to have here? Somebody, this is go bowling, yeah, 10. So 1, 3, 6, 10, 15, etc. Those are your triangular numbers. If you add these up, if you stack them in layers and make a pyramid, then you're going to get your tetrahedral numbers, which are here. If you go across the rows, let's take a look at the sum of these across the rows. It's 1, 2, 4, 8, 16. You see a pattern anywhere? What would be the next one? 32, 64, etc. There are dozens and dozens of patterns here in Pascal's triangle. Maybe I'll circle back and do just a few more, but there's a lot. Now what we want to use it for is expanding binomials. So, for instance, let's start out with example D here. And this is just a much larger version of Pascal's triangle there. One more mention about Pascal's triangle, because Antonio was asking about it, and of course Antonio left. Here's, let's see here. So yeah, here's your triangular numbers and your tetrahedral numbers. Those are what those look like. Yeah, but the Fibonacci numbers are on Pascal's triangle too, which is just really cool. There's just so many patterns there. But let's actually apply this. So if I wanted to expand this and I didn't want to multiply it by itself 5 times, then I'm going to choose to do this with Pascal's triangle. So let me see. I'm going to do that up here. Now I'm going to start it out with x to the 5th. And then what happens as I move from right to left, or left to right, with the powers of x? They're going to decrease, right? So it'll be x to the 4th, and then an x to the 3rd, x to the 2nd, and then an x. And then now we got to account for the y's. So I'll do y to the 5th, y to the 4th, y to the 3rd, y to the 2nd, y to the 1st, and then that's it. And last but not least, I've got to pick up the numbers from the appropriate row of Pascal's triangle. And that's going to be this one right here. So I want to put those numbers in as coefficients. And let's see what that's going to look like. So let's see. It's going to be a 1. You don't necessarily need to write the 1. 5, 10, 10 again, 5, and 1. And there's your final answer. That is a lot less painful than if you had to expand that out by hand. A lot less painful. Okay, so not a bad one for our first one, kind of like the warm-up example here. The patterns to take note of would be this, that you're going to start out with this term to that power and then decrease. And then at the other end, you're going to start out with that term to that same power and again decrease, this time from right to left. Nice, and that's it. That's it for example D. But they don't always stay quite this easy. So let me make sure you're comfortable here before we move on to example E. All right, I'm getting a thumbs up then from everybody. All right, good deal. Let's look at example E. Now this time I don't have such nice easy terms. I've got an X and a Y up here, but this time I've got something different. So I have to be a little bit more careful with example E. In fact, I think I'm just going to move to a separate sheet of paper here for that. Example E, 5x minus 2y cubed. Now I'm going to regard this first term as kind of like my A, back in this formula up here. So I'll regard this as being the A, and then this term as being the B. And I'm going to include the negative as part of that. So that's my B, this is my A. So when I write this out, I'm going to write it out pretty much like it's written here. I'll have an A cubed, then A squared, then A, and then on the right end, start with B cubed and decrease like I did there, except I got to put these whole terms. So it's going to look like this. We'll start out with 5A, so it means 5x cubed plus, and then what happens? Well, the exponent on the 5x term decreases. 5x squared. And then I start to pick up the b term to the first power. What am I going to put in here? Yeah, negative 2y. And let's keep going. Then leave yourself a little room here, so maybe put a plus. Leave yourself a little room because we got to go back and put in a coefficient. I've got another 5x and another 2y. So 5x and minus 2y. Josh, what are the exponents going to be on these two terms?
3 and 2, or 1 and 2.
Perfect, 1 and 2. Great. And then I need to do one more here. So let me zoom out a little bit here. What's that last term going to be? Yeah, minus 2y cubed. And I hope kind of color coding it like this helps you see where each term is coming from. There's one more thing I need to do, and I need to put in the elements of Pascal's triangle. Now, just for fun, let's start out and do our own Pascal's triangle. You're going to start out with a 1, then a 1 and a 1. Now each time you go to a new level, you add 1s on the outside But what's going to come in between here in the middle? 2. Add a 1 on the outside and put in the middle terms now. So 1 and 2, 2 and 1, 3. And that's what we need. That 3 matches up with this. Those are the coefficients that we need to fill in to kind of complete our work with Pascal's triangle. Well, at least somewhat completed. Now, if you didn't write a 1 here, I'm not going to complain. It doesn't matter to me. 3, 3, 1. Let's put in a little plus here. Are we okay this far?
Wait, so how do you know which row of the binomial to use with Pascal's triangle?
It's a good question. So this starts out with like n equals 0, n equal 1, n equal 2, n equal 3, and so on. But the row here is going to correspond to this exponent here. And another way to look at it is this one here also corresponds to that number there. So, yeah. Now, one final way that you can kind of look at things and line things up is that when you do this, 3, 2, 1, 0, you know you need 4 coefficients, and the row with 4 coefficients is this one right here. So this is kind of a double check that you get there. Last chance on this. Are we okay with what we have here? We're not done yet, though. Yeah, Rachel, please.
So, why is it just 1 5x in the beginning? Well, I know it's like 1.
It always just starts out with a 1 on either end. Now, there's a more general formula that has been proved. I think the proof for that is something that goes beyond this class. It's something called induction. It used to be part of this class, but it's beyond this class right now. Is there another hand? There is a little bit more we need to do here. For instance, if you cube out 5, you get 125. And then x also gets cubed, so 125x cubed. How about this next term? What happens when I cube out 5x, or square out 5x?
25.
Yeah, I'll get a 25. So 3, and then a 25. Is it just 25x? Thank you. 25x squared. And then a minus 2y there. Plus, again, we got that 3 and a 5x term. Nothing's going to happen to that. But the 2y term, the minus 2y term, that gets squared.
Plus
So
4y squared.
well done. Thank you. Plus 4y squared. So I've got a 5x and a 4y squared. And the last term, I could probably ditch the 1, but I'm just keeping it there so you can track things a little bit easier. Somebody I haven't heard from yet today. Jaya, what do I get when I cube that out, please? 8y cubed?
Negative 8.
Negative 8. Yeah, good. It's going to be negative 8. Let's put this all together. So that 125x cubed minus 2 times 3 is minus 6 times times 25, it could be a minus 150 x squared y. 5 times 4 would be 20 times 3 would be 60, so plus 60 xy squared, and then the last one would be minus 8xy cubed. Nice. Nice. How are you looking with example E? Is there something that you'd like me to go over a little bit more? Yes,
So
please.
just to make sure it's going to be the 2 in the parentheses that get multiplied together before the 3.
You know,
The same,
whatever order you multiply them in, it's going to give you the same. I did 3 times negative 2 to give me negative 6, and then I multiplied by 50, or by 25. If you would have done it the other way, 3 times 70, 3 times 25 is 75 times negative 2 still gives you negative 150. So whatever order you want to do. The first thing you have to do, though, is you have to square these out. Like we squared this out, we squared that out, and then you multiply. All right? Now do yourself a favor. On a test, at least get this far. At least get that far. That's half points right there. The other half is simplifying it beyond that, but at least get yourself half credit. Now, some of the ones that we're going to do here, like this next one, example F, are going to be harder than I would put on an exam, but I think you've got something like this in your homework. So let's carefully do this one out. Example F. 1 over x minus square root of x to the 4th. I'm going to make a suggestion that we start this out by rewriting it as x to the negative first and x to some power. What would that power be? To the 1/2. Good. Something to the 1/2. Now looking at the exponent, I think I need another level for Pascal's triangle. So let's go up here. You're required to know Pascal's triangle. You should be able to derive that yourself, as many levels as you need. If you're worried about that, then I've got another little thing that we can do, but for now, fill in that next level of Pascal's triangle. Zaid, what number should I put here?
464.
Nice, 464. So this is the level that we're going to need for this one down here. Thanks, Zaid. Let's again, does it help organize things for you if I do this? Yeah? All right, I got a couple. All right, I guess I'll do it again. This is going to be your A. And then, what's that?
Like your rows don't exactly line up on your table.
Yeah, sorry.
See?
And then, let's see, we got B will be right here. We're going to include the negative as part of B. We're going to have to write a little smaller on this one than we did with the last one. We'll start out with A to the 4th power. And that A is going to be x to the negative first. Plus. And I want to leave a little room here. A again. This time we need to throw in a B. And I'm going to keep kind of going here a little bit. Plus, leave a little space for a coefficient. A and B. Some more space. And let's just put in a few things here. X negative first, x negative first, x negative first, minus x to the 1/2, minus x to the 1/2, minus x to the 1/2. And now some exponents. These exponents decrease. 3, 2, 1, and then 0, which I'm not going to bother to write. But what should I put here for this last term? Just this one, minus x to the 1/2. And now, kind of going the other way, we'll start out with a 4, a 3, a 2, and a 1, and then a 0. I need some coefficients here. Syed, what coefficient should I put here?
1, 4, 6, 4, 1.
Nice. So you got half through credit on this one. So 7-point problem, you got 3 or 4 points here. Let's get the rest of those. Let me pause for a second though. How are we looking here? We okay with those? You can do those? Mr. Scarcelli? Elizabeth? All right. So it's just a matter of memorizing this pattern, and it's not that hard. Now, some of the hard part is going to come next. If I remove this parentheses, what's going to happen with these exponents? Add, subtract, multiply, or divide?
Subtract.
Subtract?
Or add.
Bifur? Multiply? All right. I think majority is voting multiply. It is multiply. 4 times that would be x to the negative 4th plus 4. And Antonio, what would the next one be?
Negative 3. X to the negative 3.
All right, x to the negative 3rd. X to the negative 3rd. And then I'm going to have a minus x to the 1/2 here still. Okay, so let's keep going. Plus 6. X to what power? X to the negative 2nd. What's going to happen when I square this term? X to the 1/2. Yeah, so 2 times 1/2 gives me 1, and when you square something that's negative, it becomes positive, so you're just going to end up with an x. So yeah, that one worked out pretty nice. And then a 4, x to the negative 1st, plus x to the negative 1st. Well, what's going to happen to this guy? First of all, let's deal with the exponent. 3 times 1/2 is going to be x to the 3/2. And is that going to be a positive or negative term? When you have an odd exponent and a negative inside that exponent, you're going to end up with a negative number or a negative quantity, so a negative there. And last but not least, I got to raise this to the 4th power. First things first, what's the exponent? 2. Nice. Is that a positive or negative? Well done. You've got an even term there. Okay, almost done here. Let me pause. There was a lot. If I went over something too fast, back me up. Wow, lots of hands. All right, let me start closest to me. Ellie, go ahead.
Well, I guess I'll ask now, but it's sort of in regards to the next step. Can we start combining some of these?
We will combine them, yeah. When you multiply things with the same base, you add their exponents. But I needed to get rid of these exponents first before I started doing this. You can't, add these and then deal with the exponents. You got to do these exponents first. So good question. Rachel, you had one too.
Why was the last one positive?
Because this is written, it has a 4th power to it, and if you raise something to an even power, yeah. So what's happening with that is if you have something to an even power, like say -2 to the, okay. Yeah, you've got an even number of negatives that cancel each other out. So, cool. And Antonio, you had one on this one as well.
I figured it out.
Okay, good. Let's finish this up. x to the negative fourth. A minus times a plus is going to be a minus, so minus 4. And then negative 3 plus 1 half. What's negative 3 plus 1 half?
3 half. No, would be 5 halves.
5 halves, yes. Now if you're looking at that going, oh man, I just hate fractions. Don't worry about it. Let your calculator do your thinking for you. That's fine. Save your brain for other things. But you can take negative 3 plus 1 half. I could type in 1 divided by 2, but I'm just going to be lazy and type in 0.5. And then you remember that, oh, my instructor likes improper fractions, so great. There you go. X to the negative 5 halves. So
I think
please don't get... What's that?
Fractions for me.
Say again?
I just realized I think that word right there, improper fraction, was the problem with fractions for me.
Improper fractions?
Improper fraction is just division. It's not wrong.
It's
Just
somehow I prefer improper fractions as opposed to the decimals. I'm not going to mark you wrong if you wrote negative 2.5 here. But if you want to keep your instructor happy, which is always a good thing to do when he's grading your exams, write the improper fraction. How about this next one over here?
6x minus 1.
Nice. Negative 2 plus 1 would be x to the minus first. Looking good there. The sign on the next one, and let's just make that look more like a positive. The sign on the next one is going to be a positive times a negative, so I'll end up with a negative 4x to what power? 1 half. Negative 1 plus 1 1/2 or 3 halves. And finally plus x squared. Great. And that's it. I mean, if you really wanted to, you could probably get rid of the negative exponents and write it as 1 over x to the fourth minus 4 over x to the 5 halves plus 6 over x minus 4. What's another way to write x to the 1/2 power? Square root of x plus x squared. So that's borderline worth extra credit. If you take and clean it up like that, I'd be really happy to see something like that. But this is okay too. I mean, if you got this far, that's mostly what I want to see.
Would we take those extra credit?
Maybe it's getting pretty close to extra credit. That might be worth an extra point there if you take the time to be really conscientious about your work. Sure. Yeah. Nice. All right. Other comments or thoughts on example F here? Pascal's triangle is really, really cool. Like I said, it has tons of properties in it. Let me see if I got one more that I can look at here. There's the Fibonacci sequence, powers of 11. If you color these kind of an even and odd, even is white, odd is black, then you get Sierpinski's triangle, which I think I've shown you that before in this course. And for Valentine's Day, you can do Sierpinski's Valentine's, which is totally cool. This is kind of cool. You can pick any point in Pascal's triangle and then multiply together the alternating numbers. So 5 times 21 times 20 gives you 2100. Or if you do 6 times 35 times 10, 2100. At any point in Pascal's triangle. And the properties just go on and on and on. So Pascal's triangle has Pascal's name to it, but here's Pascal's triangle in a Chinese manuscript back in 1303. Wow. And in Japanese in 1781. Hebrew, if you want to get me one in Arabic sometime, I'd be happy to show that one as well. But it's been around a lot longer than Pascal. He just happened to have the name attached to it. All right. So, nice. But there is kind of a drawback on Pascal's triangle. Now let me try and get at it this way. So, in example H, it just asks you for the first 3 terms of this binomial expansion. Sometimes we don't need the entire row, the whole thing multiplied out. But I want you to think about doing this. can you see a little drawback here to Pascal's triangle? Yeah. If you had to go down to row 22, wow. I mean, take a look at some of the numbers you're getting when you get down to row 10. Look, you're already up at 252. These numbers are going to get really big really fast. And it just becomes a pain to try and keep all those around. Yes, ma'am?
So if we're only doing the first three for like example H, does that mean instead of x plus 5 to the y to the 22nd, it's just really asking us to do x plus 5y to the third?
Well,
Or not?
what it's asking you to do is to know something a little bit more general than just Pascal's triangle. These numbers and the corresponding powers are actually given by this theorem. It's called the binomial theorem. And what this is a way to write these things down in general. So the coefficients come from what we started with. When we started this with combinations, that kind of stuff, we were really practicing ahead of time to get ready for the binomial theorem. So you don't necessarily need 22 levels of Pascal's triangle in order to expand something like this. So how would that look? Well, in our case, the n for us would be 22. All right, so let's just make that clear to start with. N equals 22. And because n is 22, we're going to start out like that. We'll start out with 22 choose 0. And then I want this term to the 22nd power, a to the 22nd power. And then b to the 0 power, right? What is something to the 0 power?
1.
So I'm not going to write that, all right? So let's just go to the next term. Now for the next term, this number in the denominator part, or what kind of feels like the denominator, is going to increase. So we're going to get 22 choose 1. And now it's going to be x to the 21st power, but 5y to the first power. Okay. And finally, I want to do one last one because I wanted the first 3 terms, right? So here's your first term, here's your second term, here's your third term. Try and anticipate me what I'm going to put down here. If you're watching this later, hit the pause button, see if you can't figure out what's going to go here for that third term. Nikki, what should I put here for this next term? Oh, okay. Antonia?
Would it be plus 22 over 2x 25y squared?
5y squared. Do we agree with that? Is that looking good? Yeah, nice. Now, how are you going to find these numbers? Yeah, calculator. Now, do we really need to find this one off our calculator? What do we know those always to be? 1. If you actually did figure that out, it should calculate to be a 1. But kind of an interpretation of this, if you have 22 objects and you're not choosing any, then you've made exactly one choice. All right, so that'd be one way to think of it. And how about this next one? There's kind of a pattern with this second term as well, right? Can anyone anticipate what this one would be? If you've got 22 objects and you've got one to choose from those 22 objects, how many choices do you have? 22. 22. You got 22 objects. You can pick any one of them. You got 22. So a couple of these numbers you can get just kind of by thinking about them, really. So what this ends up to simplify as would be x to the 22 plus 22 times x to the 21 times 5y. So 22 times 5 is going to be 110 x to the 21 and y. And so that leaves us with one last term to do. This one you'll probably want to do on your calculator. 21, choose 2. Choose 2. Let's see if I can't do it without it. Don't tell me. Times 21. I want to say 253, but I'm not sure. No, 283? Yeah, all right, whatever. 235? 231. So anyways, we'll type in the 22, hit the math key, probability, 22, choose 2, and bam, 231. Now that 231 is going to have to multiply something. Let's keep in mind that I've got a 5 squared and a y squared. So basically it's going to be this term here is going to end up being 231 times x to the 20th times 25y squared. 231 x to the 20th times 25y squared. I would like you to multiply out that 25 times 231. So let's do that. The easiest thing to do, the user-friendly thing to do, is just hit the times key and then multiply by 25. So there you go. 5,775 x to the 20th y squared. And just about ran out of room there on my paper, but got just enough. Yay! There's your first 3 terms. Can you do that? All right. I'm going to change up example I just to make it a little bit more user-friendly. Let's put the x over here. It just, yeah. Otherwise, you're going to have to calculate, you know. So let's make that just a 2 and put the x here. Yeah. So 2 plus 7x to the 18th. And I want you to do the same thing. I want you to expand this and show me the first 3 terms. So there you go. Start out kind of like what we did here. What's n for us in this case? 18. So you got a different n to work with, but overall it should work out the same-ish, you know, same kind of procedure.
Yep. So 2 to the 17th here. 17th, plus
No, not plus, times.
times 7. Right.
Oh, yeah. Appreciate it. Spend it like that.
Yeah, I forgot. I should have made that like an X plus 7y or something like that. Yeah, we're gonna get some really big numbers here, aren't we?
So I
Sorry.
kind of stopped.
I
writing.
realize, it's okay, we can deal with big numbers, we don't have to do them out, by hand, fortunately. But let's get the format down. What I'm realizing, when I change things up, I'm like, yeah, I didn't want 7 to a really big power, but then I forgot that, oh yeah, 2 to the 18th is also a really big number. It's probably like, what, a 250,000-ish?
260.
Yeah, 260 something. In any case, so the first term should look like this. It should be 18, choose 0, and then 2 to the 18th, and then 7x to the 0. I'm going to ignore that part. And then the next part would be 18, choose 1, 2 to the 17th, and 7x to the first power,
You got
It's 2 to the 7, not
2
7.
to the 7.
17th. Thank you.
Also, 2 to the 18th is 262,144.
Thank you. It was on the tip of my fingers. Let's put that in a minute. And finally, 18, choose 2, times 2 to the 16th. So the powers on the 2 keep on decreasing, and the powers on the 7x increase. So I guess the way to do this in a user-friendly way would be to make this just a variable, like, a plus 7b to the 18th. That way you don't have some humongous number here. Now, 18, choose 0. That's just going to be what?
2 to the 18th.
It's just going to be a 1, so 2 to the 18th. You see what, 262,000?
144.
262, 144?
Yeah, 262, 144.
All right, 262, 144 plus. And now over here, 18 choose 1 is going to give you an 18 times 131,072. If my math is any good. 131, 1072.
Yep, that's 2 to the 17th.
And finally, 18 choose 2. Is that 163? Did anyone get that one out? 153? 153, yeah, thank you. So 153, 2 to the 16th, it's going to be what, 65,586?
36.
36? Yeah, there we go. So 65, 536.
536, yeah.
Thank you. And then times 49 x squared. All right, I'm going to bust out a calculator for a couple of these last ones here. Let's see. So this one, that one's going to stay the same. That's just going to be 262,000. It'd be nice if these things. 262, 144 plus 18 times 7 times this. Yeah. 18 times 7 times 2 to the 17th. Woohoo! 165, 150, 072.
X.
X. Yep. And finally, this last one, let's see, 53 times, that was 2 to the 16th, times 49. Oops.
Where did you get the 153 from?
18 choose 2. I think it turns out to be 9 times 17 should give me that. All right, so try again. 53 times 2 raised to the 16th.
It's 153.
153, thank you. Times 49. Whew, that feels kind of big. Is that what you guys were getting? All right, plus 491, 323, 392. X squared. Wow. Whew. Nice. All right, like I said, this is a little bit of a learning lesson for me. I think if I wrote a problem like this on a test, I'd make that a variable. I'd put it more like, you know, x plus 5y to the 13th or something like that. That way you don't have such really big powers of some number there. It's just going to be x to the 13th. So, any other comments? Were you guys able to get that one for example I? Let me see some hands. Did you get example I? That one worked out okay? All right, good deal. Last but not least, Rachel, you were talking about the Mega Millions earlier today, right? All right, let's go back and take a look at that. So that's a lottery type problem. And let's see, how to play the Mega Millions. All right, so players may pick 6 numbers from 2 separate pools of numbers, 5 numbers from 1 to 70, and 1 number from 1 to 24. So 5 numbers from 1 to 70, let's do that. And then we'll finish it off with the 1 from 24. And that'll tell us how many possible winning combinations there could be from something like this. So Mega Millions. So first thing we need to do is calculate 70, choose 5, because you're going to choose 5 numbers from those. And then, what was it, 24? Or was it 26? It's 24. So you got 24 to choose from the next pot. So we need both of these numbers. So let's see if we can't find those. This is just our combination stuff. This is the stuff that we were learning with just a minute ago. So let's see. 70 choose 5. Should be a pretty big number. 70 choose 5. 12 million. Woohoo! All right, so the first one is going to be 12 million 103,014 times. Well, the second one, do I really need to do 24 choose 1? If you got 24 objects to choose from and you're only picking 1, how many choices do you have? 24. So yeah, so times by 24. Now the convenient thing to do on your calculator is to multiply by 24 just by hitting the times key. And the nice thing that hitting the times key does is says, oh, I'll just take this previous answer and multiply by 24, and there you go. So how many winning Mega Millions combinations could there be? About 290 million. And as Rachel pointed out, the price of Mega Millions went up. It's no longer the bargain at $5. It's $7. Woohoo! All right, 472, 336. So if you had 1 ticket, your chances of getting struck by lotto are less than your chances of getting struck by lightning. Yeah. So it's a tax on the mathematically challenged, but hey, please play. It supports your state's education system.
As long as they
Does
don't
it
teach
actually?
What's that?
I said as long as they don't teach you any stats.
Yeah, yeah. Well, that class is in the fall. If you want to learn what that permutation key does for you, it's different than the combinations key. Then take my stat class in the fall.
Actually,
But-
is that just an unhinged conspiracy, or is
What, that?
the lottery kind of lobby to ensure that like stats education is
Oh, I don't.
in primary?
I'm not aware of any such conspiracy. Although
It's
I wouldn't be
unlikely.
shocked.
Doesn't
but-
require a conspiracy to have the interest
Yeah.
in something.
In any case, at least you guys know. Curious enough, the Powerball does things a little differently. They do things 69 balls, but then you have to choose 1 out of 26 here. So which one's better? If you had to play and hope that you were going to win one of them, which one would you play? So let's just try this again. We'll hit the, let's see, 69, math, and there we go. Choose 5. So 11 million, but this time we got to multiply by 26. What do you think? Is it going to be higher or lower than the Mega Millions?
Higher.
Higher? All right. Pretty close, but a little bit higher. So 292,201,338. So 292, 201. What was the last few digits? 338. Thank you, 338. So yeah, take your pick. All right. Your chances of winning are about the same if you play or don't. So, yes,
You
question?
go on the Michigan lottery website and it'll tell you for scratch offs how many winning ones are still in circulation and haven't been won
Oh,
yet.
that's
So
interesting.
If you go and look at the ones that have the most in circulation that are winning,
That's pretty smart. That's pretty cool.
My
Yes.
grandma did a lot of scratches, and she never got a super big win, but she got a few where she got over 100. What's the likelihood of that?
That I don't know if it's something you can calculate. You'd have to know how many were distributed by the lottery.
Okay.
So,
You're
good question.
most likely to win when you get somebody that hates playing the lottery to go buy tickets, and they always win. No matter